Hello, welcome to DS 2810, Lecture 1. So, the this class is about the mathematics of data models. So, we're going to start this class by talking about what we can imagine what a vector is. A vector, where I would like you to start, is I would like you to think of vector as a set of numbers, just a bunch of numbers enclosed by a bracket. In data science, normally the notation for vectors is a lowercase letter, either cursive or bold. Most of the time, you will see a cursive letter. And the vector is represented, like I said, a bunch of numbers enclosed in a bracket. And for the notation we're going to use here, the standard is that when we think of a vector, it's going to be a vertical vector. Okay. Now, once we know something is a vector, we also need to know the dimension. The dimension of the vector is denoted with this notation. What this is saying is that the vector x is an element of real numbers as opposed to complex or imaginary in 3 dimensions. So this 3 dimension tells us essentially there are 3 numbers inside a vector. Consequently, if we look at this one, it's only 2 dimension, therefore there are 2 numbers. Not rocket science. So, of course, the only thing that really matters is that for vectors, the notation we're going to use is in lowercase. It doesn't have to be x, it could be y, or it can even be Greek letters. Okay? So a vector by itself doesn't really tell us anything. If I tell you a vector is 153, that's not that helpful because you don't know what that means. It just seem to be 3 random numbers. We, humans, we need to attach some kind of meaning. Once we have attached some meaning, then things start making sense and we know what to do with it. So, for example, for these 3 numbers, it could be the XYZ coordinate of a rocket, for example. Or it could be the number of points scored by 3 people in a board game. Or it could be the number of people you dated last 3 months. Essentially, the possibilities are endless. So a vector by itself doesn't really mean anything. We have to essentially give it some kind of meaning. Once a meaning is given to a vector, then the vector is no longer just a bunch of numbers. It becomes data. And with data, we can now do something interesting with it. So let's give it some meaning. Those same vectors of 3 numbers, we're going to say they are the scores of 3 soccer teams: United States, Brazil, and Canada. Now, these numbers are no longer just random numbers, but now they mean something to us. And once a vector, we can view vector as data, we can start posing various queries, questions about it, such as what is the highest score, the lowest score, the average score, vary any question you want, really. And we can mathematically represent these queries as some kind of symbol: Q1, Q2, Q3, question 1, question 2, question 3. So once a vector becomes data, we can then use query to extract some kind of meaningful information. So question takes the data, extract some kind of meaningful number. We can translate query into mathematical language, where query takes some vector and returns some kind of meaningful number. Here, query is kind of like a function that takes a vector and extracts some kind of meaningful. Now, historically, if you are like a freshman, sophomore, when you think of functions, you're thinking of something more like this, where you have a point and there's a value. But in this case, we're now thinking more like, well, there's some kind of data, and the function is extracting information from some kind of vector, which is a different way of thinking about functions and vectors altogether. So here, let's use Q1, right? Which is equivalent to finding the maximum value. So the max of x is equal to Q1, where we put the original vector in there. Now we put this vector in, and obviously the largest number is 5. Q2, the smallest number is 1. Q3, the average number is 3. So we are putting vector into a function, and we're extracting information out of it. So that's yet a different way to think about functions. Now, a function acts as a query that takes x and returns some kind of meaningful value. Okay? So function takes this, returns some kind of meaningful value. It doesn't actually have to be just one value. It could be multiple values where it has the output. Here's an example where we have a function that takes 3-dimension output 3-dimension. So we have function, it takes 3 inputs, x, y, z, okay? And it actually outputs 3 things, 1, 2, 3. Let's do a quick example. Let's say we have a function and we input the 3 values 1, 0, 0. And now we put 1, 0, 0 here, 1, 0, 0, 1, 0, 0, and it returns 3 values, 2, 2, 1. So the output is the vector itself with 3 values. Now, when you are taking like calculus, multivariate calculus, we are actually used to seeing notations such as this, where the input are various letters of the alphabet. However, in data science, we have inputs that are in very, very high dimension, thousands, even millions of input, possibly. So we don't have enough letters of alphabet to essentially represent it. So another notation to show you represent the exact same equations is this. Instead of saying x, y, z, we have x1, x2, x3. So once we put the numbers in, we can essentially represent as many as possible. So these two are exactly the same notation, just represented one labeled by number, other one labeled by letters of the alphabet. So you will see both notations. Okay? Now, functions can have multiple dimensions for input and output that we just saw, right? We saw one that was 3 dimensions. Now, we can now picture a potential space where every single point is the possible input for a function. So this is point, this point, this point, every single point here. And the space taken up by every single point that could possibly be the input of a function is called a domain. And the space of every single possible output that could be the output of a function, like this function, is the range. So the domain and the range, they don't have to have the same dimension. Okay? You can have multiple dimensions for input, but only one dimension for output, or multiple dimensions for output. And the way you can represent the dimension of the input and output given a function f is through this notation. So this is an important notation that you will see. This says right here that we define a function such that, so this symbol right here is such that the input takes 2 dimension of real values, r for real, and outputs 1 dimension. So if it doesn't say anything, that means it's 1 dimension of real values. So this is what this notation is for. Now, I would like you to pause the video very quickly now and see if you can answer these questions. Okay, I'm going to continue. Hopefully you paused it. So we actually just did this. X and Y, the space between them are called domain and the range. Now, given X input and X2, what is the input dimension? So you see, there are 2 of them. So the input dimension should be 2. Now, given this notation, what's the input and output dimension? So again, you read the notation 2 and 1. So input 2, output 1. Now you have multiple numbers in a bracket like this. It's called a vector. Okay, this is a vector. We're not getting into the geometrical or the mathematical definition of a vector yet. But for now, suffice to just think of it vector as a vertical column of numbers enclosed by a bracket. Okay, given x is this, and f of x is equal to this. So the assumption is that the first one is x1 and the second one is x2. Now, if you plug this in here, then it would be 1 minus 3, which is equal to minus 2. Okay? Not that difficult. Okay? When you read this, what does the symbol stand for? Now, this is very important. You see this all the time in like data science. So this symbol is such that. And now we have a vector. How many dimensions this vector? 4. Okay? 4 coming from this. Okay, now let us move on. Now that we kind of know what a vector is, let's talk about addition. How do we add two vectors together? So if we have x equals to this and y equals to this, when we add x and y, it's equivalent to the two vectors added together. Now, how do you add two vectors? It's actually very, very simple. You simply align them, the numbers. The first one add to the first one. 1 plus 2 is equal to 3. The second one add to the second one. 3 plus 2 is equal to 5. And that's it. And the same idea carries over for subtraction. You align the first one. 1 minus 2 is minus 1. And 3 minus 2 is 1. Now, geometrically, when we're adding vectors together, so let's look at this more closely. We have 1 and 3, right? 1 and 3. If we plus by 2, 2, 2, 1, 2, 1, 2. So the final vector from the summation of these vectors right here. And you can see this is 3, 5, which is equivalent to this. So vector addition is essentially adding up vectors and getting a resulting vector right here. Vector subtraction, in the other hand, if we had added 2, 2, it would have gone this way, similar to this. But instead, if we're subtracting 2, 2, what's happening is instead of adding this, it's adding the opposite direction. So the subtraction here is pointing directions. So the final result will be this vector here, which is negative 1, 1, exactly as you see. So addition and subtraction of vectors are really, really easy. Just align them and then add them together. Another operation I want us to learn is called the transpose. When you have a vector x, the transpose is when you add a little t on top of it, the transpose symbol. Now, transpose is really easy. If you have a vector that's vertical, after transpose, it becomes horizontal. If you have a vector that's horizontal, after you run the transpose, it becomes vertical. So you can see from here, we start with a vertical vector. If you perform transpose on the vector, it becomes a horizontal vector. Again, here's the 3 by 1 vector. You perform the transpose, it becomes horizontal. And if you happen to have a horizontal one already, then if you perform the transpose, it becomes vertical. So from horizontal, it goes to vertical. From vertical, it goes to horizontal, basically. So that's the idea of transpose. Okay? Now that we've done transpose and addition, we can start looking at multiplication, various type of products. Okay? And the first one, which is the easiest one, is called the Hadamard product. The symbol for the Hadamard product is just a dot inside a circle. Now, to perform Hadamard product is just like addition and subtraction. You align them, the first to the first, second to the second. And then you simply multiply them together. 1 times 2 is equal to 2. 3 times 2 is equal to 6. And that's it, basically. Now, that is the easiest product. The next one is called the dot product. I think I wrote product twice. Okay, dot product. Now, dot product is written with a dot right here. It's also written this way, where you have the transpose of x times y. Now, if you have the transpose of x times y, then when you write out the actual vectors, a dot product results in this operation. Now, you might ask, okay, how do we multiply them together? Well, it's actually you take the first one and multiply the first one, second one, multiply the second one. Very, very much like this. First times first, second times second. However, in a dot product, it is different in that once you multiply the first times the first, second times the second, you add everything together. So you would essentially do a Hadamard product and then you would add them together, which is equal to 8. So the Hadamard product will give you a vector of the same dimension. However, a dot product is going to give you just one number because you are essentially adding all the numbers into just one. So, dot product. Next, we're going to learn this thing called inner product. This should not be here. The inner product is written this way. Basically, x and y in brackets. The inner product is actually, in terms of its mathematical operation, can also be written this way, which is equivalent to the dot product. So you can actually think of dot product and inner product basically the same for the purpose of this course. They're not exactly the same, but close enough. For the 90% of the time that you will ever encounter in your life, they're going to be the same. So since it's exactly the same operation, they're going to get the same results. Okay, so now that we have done Hadamard, dot, and inner product, let's do an outer product. Vector outer product. So with the same vectors, the outer product symbol is an X with an inside a circle. Now it's also written this way. Now notice the inner product was this, where the transpose is on the left term, but the outer product, the transpose, is on the right term. So here you will write it this way. Most of the time, we don't even need the symbol. We simply write it this way. So this is gone. You don't even need this. And the way you will perform outer product is you take the first number, which is 2, and you multiply by the entire vector here. And that will give you the first column, 2, 6. And then you do it again. You take the second one and multiply by the entire column. And that will give you the second column, 2, 6. Okay, so let's do this one more time for another more complicated. 1, 2, 3, 0, 1, 2. Okay, so you take the first value and multiply by the entire column, which will give you 0, 0, 0. Now you take the second value and multiply by the entire vector, which will give you 1, 2, 3. Now you take this third one and multiply by it, which will give you 2, 4, 6. That is how the outer product works. Okay. Now, one final multiplication. So we've done a lot of multiplication. What if you have multiplication by a constant? So let's say you have 1, 3, and you want to multiply by 2. What does this mean here? This is also very easy. You simply take the 2 and multiply each one of them, which results in 2 times 1, this is 2, 2 times 3, which is 6. So that's it. This is multiplication by a constant, alpha. You take this and you simply multiply each term. Okay, now I would like you to pause the video and try to do it. There are a bunch of operations here, and see if you could do it. Okay. So pause the video. Okay, so I hope you paused the video and was able to essentially do these questions. So let's move on to the next topic, which we're going to talk about how function could be either linear or nonlinear. Okay, so linear, nonlinear. Well, linear functions, we essentially are have the characteristic of easy to work with, easy to use, and even though it's less accurate, it's still really useful most of the time. It can very often be used to approximate nonlinear functions. Now, nonlinear functions are harder to understand, not as easy to use, but it's more accurate. So for this class, we're going to really focus on starting off. You got to start somewhere. And let's start with the simpler functions called the linear functions. And first, we need to be able to show if we are given a function, we would like to prove that a function is linear. And the way to prove that is that if a function is linear, if it satisfies two conditions. So this is essentially a test you want to run that if you run this test, you're guaranteed to know whether a function is linear or not. And the first one is that let's say you have two vectors, x and y. Okay, if you add them up together, and then you plug it into the function, if this is equivalent, this is the same as if you take x, y separately, plug them into function, and then add them together, then the first condition is satisfied. So this is the first condition. If you add up x and y first versus adding them afterwards. The second condition is if you input x, if you multiply x by some kind of constant, alpha, that's equivalent to plugging x into the function first, then multiply by alpha. So this right here is the standard way, the official way of how you can prove that a function is linear. Since this entire course is about linear functions, it would be nice that you know how to distinguish linear functions. So let's do a quick example. Right here we have a function, okay? So the input is x, which x is two dimensions, x1 and x2. The first value, x1, will go here, and the second value, x2, is going to go here. Okay? Now, let's try to prove it. Instead of using x, let's do z and y. So we invent two other vectors. And we can prove that this right here is linear if we add up z and y first, then put it into a function. And that is equal to putting z and y into the function first, then add them up. Okay, so let's see if they're the same. So if we add z and y, that's just z1 plus y1, z2 plus y2, from what we learned previously. So let's plug this in. If we plug this in, this is the first value. So the first value is going to go to here, right? So this goes right here. And this is going to be the second value, which is going to go right here. So 2 times the second value. So that's what we get. Now, let's try to put them in separately. If we put them in separately, then it'll be z1 plus 2z2, right? Instead of x1 plus 2x2, we plug z in, z1. Similarly, y1 plus 2y2. Now, if you just rearrange this term a little bit, notice that you will end up getting the exact same as this. So they're the same thing. And after this, we can now run the second test. So because they're the same, test number one, check. Because they're different, because this the first condition is passed, we now need to test the second condition. The second condition is now we're going to put alpha. We'll have some kind of vector x, and we're going to multiply by alpha and plug it into function and see what happens. So if you multiply alpha by a vector, it's equivalent to multiplying each element by alpha. And now this is the first term, and this is the second term. We can pull alpha out for each one of them. And now notice that this is exactly equal to f of x. See? Exactly the same. Take a second look. So we can now replace this with f of x. So we have now proven that that if you plug the alpha in first, is equivalent to multiplying by alpha afterwards. Okay? Now, here is an example of nonlinear function. Why don't you pause the video and see if you can follow through the same logic. And notice that it essentially would fail the first test. And when that fails, we can now say this is a nonlinear function. So yeah, pause the video for a bit and study this. Okay? Now, again, you want to pull out a piece of paper and see if you can follow the same logic and see if you can prove that these are either linear or nonlinear. Okay? Pause the video and try again. Now, there are actually a couple really quick rules of thumb to identify linear and nonlinear functions. On the exam, I would expect you guys to be able to prove it. But if you're just looking at it for yourself, you can tell something is linear if you have the variables clearly separated, connected by either addition or subtraction, and just multiplied by some constant. If this is the case, this would be linear. You can just kind of look at that. Now, if the terms, for example, are multiplying each other, then that's not linear. Okay? If you x2 times x3, that's not it. Or if you have some kind of power or some kind of function of x, like sine of x1 plus x2. So this will be a problem. Or any real nonlinear function like log, because sine and log are obviously not linear. And if you're having such a strong nonlinearity in your function, that's no longer linear. And we can see this very quickly, that these two are clearly separated, combined by addition. Over here, we have a power, so you can't have power, or you can't multiply them together. You can't have signs, functions of it. This one is pretty good. This is exponential, so that's not linear. This is exponential and like a multiplication of variables. Here, square root, that tells you it's not. And here, square root is obviously not. Okay? Now, this is how you will represent vectors and matrix in the code. You want to essentially study this and make sure you're able to understand the notation. This is how you essentially create a vertical vector. This right here is how you create a horizontal vector. Once you create a vector in Python, you're able to calculate the addition, summation, bunch of operations simply by writing like addition, right? So this will give you the result. If you remember from previously, this is the same result. Or we can do the dot product. So we're not going to get to the matrix for now. But over here, this one is the Hadamard product. So you want to perform these exercises and make sure you can do them. If you don't have Python, make sure you have Python as well as Numpy. Ask the TA for help. So once you have done this, you want to make sure you can use Numpy and essentially perform all of these operations. Play with them, and really learn how to do them. So that's it for today. Thank you very much. You have a good day.